Hey friends, what we're going to take a look at in this lesson is something known as differential equations. What's nice about what we're going to do today is we're going to take care of one of the questions that you might have had as we were dealing with indefinite integrals. So remember when we take the antiderivative of something or an indefinite integral of something, we end up with this plus c, this constant of integration it's called. So what we're going to do today is we're going to figure out one way that we can get rid of that plus c, that constant of integration. So what is a differential equation? Well, really a differential equation is used when we're trying to relate variables to different rates of change. It comes up a lot in physics and in different applications of mathematics. So it is really, really important. You know, you can take entire courses on it in university if you want to go that route. You know, I took a couple when I was in university, 300 and 400 level courses, all just about differential equations. So just something to keep in mind that there are some really robust applications. The nice thing for us, friends, is that these questions actually are pretty nice and easy. So determine the curve y is equal to capital F of x. Okay, so the antiderivative is what I'm saying there, that passes through 2, 3 and satisfies, well, the derivative dy dx, so the rate of change. So what I've got here is some rate of change is this polynomial function. So what I'm going to do is I'm going to take the antiderivative of this, or the indefinite integral, same. So I'm going to go and I'm going to say, okay, the antiderivative of this is capital F at x. Remember what we do, we add 1 to the exponent, divide by, hopefully you're getting good at that now, right? You've trained your brain to kind of work backwards, right? Like that. And then don't forget, it's this constant of integration that's in our way. And we'll just simplify that up, right? Clean it up a little, 12 divided by 3, and so on and so forth. Okay, so now it's this plus c, which gives us, remember, this constant, it gives us what was known as the family of curves, because we don't know what that c value is. So it will give us all these vertical translations. Well, if I want to find what c is equal to, what I'm going to do then is I'm going to sub in my initial condition. And my initial condition was this point 2, 3. So I'm going to sub that in. So y is 3, the output's 3, the input is 2. And from here, friends, all we've got to do, and I screw this up all the time, is just simplify for c, right? It's funny how the little things can sometimes be the things that you mess up, right? And so given that what I just said, I'm going to try and take my time with it just a little bit. And so I get a c value of negative 39. So what was the curve that we were looking for? Well, the curve that we were looking for then was this. And let's do it in hot pink because we don't have enough hot pink in our life. Curve then was 4x cubed plus 2x squared plus x minus 39. And again, you can check your work by taking the derivative of the antiderivative has to give you that original function. And what you'll find is that negative 39, which was that constant of integration right there, it doesn't have an effect. That could have been plus a million. We don't know. We still end up with f of x. But for this one specific curve that passes through the point 2, 3, it's unique to that situation. All right, friends, there it is. A short one for you.